Hello, this is Mr. Weideman, and we're going to work together on problem number 71 on page 114. This is a free fall problem. A ball goes up and then it goes back down, and it asks how high did the ball go. We're not given a lot of information here. We're just given that the total time in the air is 6 seconds. There is something else that we know. We know what the acceleration of the ball is going to be. We know that it's acceleration moving up, and we know it's acceleration moving down. It will always accelerate at negative 9.81 meters per second squared, or what we call little g. Now, we kind of fool around with this in class just a little bit, tossing a ball up in the air and looking at its motion. And let's do that here. I've got a cheesy little video that we can watch for a ball toss. Okay, the green dots here is a video analysis. Each dot represents upward position versus time. And we can make a plot of that data, which is what we have right here. And what we can see is the slope is positive yet decreasing. When the ball reaches its max height, the slope becomes 0. Then the slope starts increasing in the negative direction. Okay, if we look at this on a velocity versus time curve, that's this right here, we can see that the velocity starts out right here, decreases to 0, and then increases in the negative direction. And we can see that the magnitude of the velocity here and the magnitude of the velocity here is about the same, just in opposite directions. Okay, and this makes sense. The ball slows down, comes to a stop, increases in velocity in the negative direction. Okay, now let's use this information to help us solve our problem. Okay, so what we have here is we have our ball thrown up initially. Notice that the velocity vector is going up until the velocity reaches 0 at maximum height, something that we call the apex, and then they increase again in the negative direction. We can also take a look at the amount of time. This is why I call this the what comes up, what must come down problem. Whatever happens on the way up has to unfold in the opposite direction on the way down. So the velocity must decrease to 0, and then from 0 must increase back to its original amount, just like we saw in the little cheesy ball toss analysis. Okay, so what we now have is we now have this time that it takes the velocity to go from what its initial point is to 0 and back to 6 again. All right, but the problem is we want to find out exactly how high up this thing goes. All right, well, we've taken care of the time. We know what g, or the acceleration, is, but we're stuck with, well, what's the initial velocity? I need to know that before I can calculate my upward distance. Well, the key is this right here. We need to look at these two velocities, the initial and final. We know that they are equal in magnitude, but opposite in direction. So what we can do is we can just say, well, v final is the same as v initial, just the negative of the v initial. So let's take one of our magic 5 equations. V final is equal to v initial plus acceleration in time, and substitute in. V final is just a negative of v initial, and acceleration is just negative g. We do a little algebra, and I solve for v initial, plug it back into my distance up equation, and then I can solve. Notice down here I use t2 total instead of T up? Why do I use 6 seconds instead of 3 seconds? Because V initial and V final are separated by a total of 6 seconds. V final becomes the same as the negative of V initial only after 6 seconds. After 3 seconds, velocity has become 0. So that's why I use T total instead of just T up to get the initial velocity. And once I have the initial velocity, plug that into my distance up equation, use 3 seconds for my time up, and then I can have my max height. All right, I hope this works well for you.